Are you a college student who is introduced to Cisco certifications? Or are you a fresher who wants to be a Cisco certified candidate? Do not worry, I'm here to help you. Hi, I'm Laksh and I'm a network engineer with 11 years of experience and 3 years of training experience. I have completed CCNA, CCNP, and the prestigious CCI as well. And I'm passionate about teaching others about these courses. I have trained many candidates who are working in companies like Cisco, Amazon, HP, Juniper, and Calix, and such other companies. So, if you want to start your journey in networking and dream about working in these companies in future, then join my course of CCNA plus CCNP starting in the month of February. For more information, contact on the number below.
So in the last class, we started our discussion on OSPF on Ethernet interfaces, right? And with that, we discussed what is a problem. We also we discussed what is a problem of the informations being spread, or the database, or the hello messages that are being sent across a particular network in an Ethernet environment. What are the complications that we may see, and to avoid those complications and to keep everything or the flooding of the hello messages less, or mitigate the flooding of hello messages, we introduced two new devices called as DR and BDR. Right? We discussed about what is a DR, and DR is a device in a network or in a Ethernet network which has the highest router ID, and BDR is the second highest router ID router, right? So all the devices in the Ethernet OSPF network will have adjacency only with the DR. The non-DR routers will have only adjacency with DR. So in our scenario over here, DR and BDR, right? R4 was the DR and R3 was the BDR, right? So R1, R2 will share, or R1, R2, and R3, all three of them will have adjacency with DR. R1 and R2 will, okay, they are called as DR other routers, right? So R1 and R2 will share their database with DR only, right? R3 and R4 will have full adjacency between each other. R1 will have full adjacency with R4. R1 will have full adjacency with the BDR as well. So it's basically what we learned in the last class was all the DR other routers will have full adjacency with the DR and the BDR routers. The DR other routers will not have full adjacency with DR other routers. Okay, so this is what we understood. And any messages that is sent at the any messages that is sent by a DR other router will be sent at 224.0.0.6 multicast address, which is DR only multicast address. And when the DR receives that particular message and or data and wants to share it with other OSPF speaking routers, it shares that information at the multicast address of 224.0.0.5. This is what we saw. So in today's class, let's do a small practical of that in order to understand this concept better. So over here, we can see that. So over here, you can see that there are 5 routers. Okay, R1, R2, R3, and R4. These are the 5 routers that we have in the diagram. They all are connected through a switch. Okay, and we can see the loopback addresses 1.1.1.1, 222, 333, 444, and 555 of each routers, and their interface IP addresses as 10.0.0.1, 10.0.2, 10.0.3, 10.0.4, and 10.0.5. These are the IP addresses of those routers. Okay, so what we understood in last class was, in such an environment where all the routers are connected through a switch, the OSPF considers such kind of network as a broadcast network, as a broadcast network. Okay, or we understood in the last class that an OSPF considers an Ethernet interface. It can be a normal Ethernet interface, it can be a fast Ethernet interface like this. It can be a gigabit Ethernet interface. It can be a 10 gigabit Ethernet interface, or it can be a 100 gigabit Ethernet interface, but it can be even be a 1000 gigabit Ethernet interface. It's an Ethernet interface. So OSPF thinks such interfaces as broadcast interfaces, and we understood why OSPF thinks so. All right. And in such an environment, we know that we discussed that a DR is elected and a BDR is elected. And in this scenario, the DR will be the router which has a highest router ID. And we know that router ID is elected based on whichever router has the highest loopback address. Okay, whichever router has the highest loopback address. And if this loopback address is not present, then whichever router has the highest IP address, physical IP address, that router will be chosen as that a particular IP address is chosen as the router ID. And whichever router has the highest router ID, that router will be chosen as the DR. And in our diagram over here, 5555, you can see 111, 2, 3, 4, and 5. These are the loopback addresses of the respective routers. So R5 has the highest router ID, and hence naturally R5 will become the DR, and R4 has the second highest router ID, and it will become the backup DR, or backup designated router, and a backup designated. All right. And we also learned in the last class that all the non-DR routers, okay, these non-DR routers are called as DR other routers. Okay, DR other router, DR other router, and DR other router. Okay, so these DR other routers will form adjacency with the DR and the BDR. Okay, so they will form adjacency only and only with DR and BDR alone. These DR routers will not form adjacency amongst each other. They will form the adjacency, or they will go into a full state only with the DR and BDR alone, no one else. That is the DR other routers. Okay, so let's check these things on the routers over here. So I have already enabled OSPF on all these routers. I have enabled IP addresses, and I have enabled OSPF on all these routers. Okay, so the first thing that we discussed in the last class was OSPF considers fast Ethernet interfaces as a broadcast interface. So let's check that. So to check that, we will execute the command show IP OSPF interfaces. Okay, show IP OSPF interfaces on R1. So you can clearly see we have enabled OSPF on two interfaces. One is the loopback address, and the other is a fast Ethernet 0/0 interface. We are checking this on R1. Okay, we are checking this on R1. So you can see here that okay, fast Ethernet link is considered as a broadcast interface. You can see the network type. Network type is called as broadcast. And this is what I was trying to tell you guys, that OSPF considers Ethernet interfaces. It can be any Ethernet interface. It can be a fast Ethernet interface. It can be a gig Ethernet interface. It can be a 10 gig, 100 gig, or 1000 gig interface, Ethernet interface. The network type that OSPF considers for Ethernet interfaces is broadcast. And hence, the concept that I was trying to tell you is, even if there are only two routers, that are connected, but they are connected using an Ethernet interface, OSPF considers this as a broadcast link, and even though there are only two routers, there will be a DR and BDR election that happens between R1 and R2. Okay, so we were discussing serial interfaces, right? We did not see any such kind of DR and BDR election on a serial interface, because on a serial interface, OSPF has the network type as point to point, but on an Ethernet interface, you can see the network type is broadcast. So if you connect R1 and R2, using an Ethernet link, it will consider it as a broadcast interface and it will elect DR and BDR between R1 and R2. Okay, this is what I was trying to explain you, the network type as broadcast. Okay, and another link or another link on which we have enabled OSPF is loopback 1. So these two are the interfaces where we have created OSPF. Okay, so as I was saying, on this particular topology, R5 will become the DR. Okay, R5 will become the DR. So on R1 itself, you can see it says the neighbor count is 4, but the adjacent neighbors count is only 2. Okay, what does neighbor count mean? If you remember our discussion on the OSPF states, right? OSPF states, I explained that when two routers go into a two-way communication or they move into a two-way state, they are called as neighbors. But when they move into a full state, they are called as adjacent, right? So we can clearly see here, it says the neighbor count is 4. Out of those 4, the neighbor count is 4. Out of those 4 neighbors, only 2 of them are adjacent. Okay, so let's check that, or let's try to understand how. For R1, how many OSPF neighbors are there? 1, 2, 3, 4. So this statement is right. Neighbor count is 4, correct? And it says out of those 4 neighbors, the adjacent neighbors are only 2. Okay, and what are those? We know that R1 is a DR other router. Okay, it will form adjacency only with the DR and BDR, and that is why the adjacency count is 2. Okay, and you can clearly see it says R1 clearly says who is the designated router? 5555, that is R5. Who is the backup designated router? It is R4. Okay, so you can automatically see that R5 has become the DR, R4 has become the BDR. Why? Because R5's router ID is higher, R4's router ID is the second highest. That is why they are the DR and BDR respectively. And what are their states? Let's check. Okay, show IP OSPF neighbors. Okay, you can clearly see here that R1, we are on R1. R1 has formed a two-way state with R2, a two-way state with R3, but a full state with R4 and R5. And that is what we see here. Neighbor count is 4, right? You can see the neighbor count is 4. There are total 4 neighbors, but out of those 4 neighbors, only 2 neighbors are adjacent. That is the DR and the BDR. And you can clearly see it says R5 is the DR and R4 is the BDR. And you will find the same information across all the routers. Okay, so let's go on R2. Okay, show IP OSPF neighbors. You will see R2 has formed two-way state with R1, two-way state with R3, but full state with R4 and R5. Similarly for R3 as well. Show IP OSPF neighbors. We can see it has formed two-way state with R1, R2, but full state with R4 and R5. Okay, let's go on R5, which is the DR. Show IP OSPF neighbors. Right, and you can clearly see that it says it has formed full neighborship with all the routers because it is the DR. Since R5 is the DR, it has formed full neighborship with all the routers. The same thing applies for R4 as well. R4 will also say, I have formed full neighborship with show IP OSPF neighbors. It has formed full neighborship with all the routers. You can see full. All the routers have formed full adjacency with DR and BDR. Right, DR and BDR. So Now, we also discussed one more thing in the last class, that if the DR fails, BDR will become the DR, right? If DR fails, if DR fails, right, BDR will become the DR. And when BDR becomes the DR, there will be an election for a new BDR. And in this case, R3 will become the BDR because it will have the second highest router ID. All right. So let's try to fail R5. Okay. So configuration terminal, I will shut down the interface fast Ethernet 0/0. Interface fast Ethernet 0/0 shut down, and we will wait on R1. Okay. So show IP OSPF neighbor. Okay. So it will wait for 40 seconds. And what is that 40 seconds? 40 seconds is the dead timer. Okay. You can see at every 10 seconds, all the other neighbors are resetting their timer, their dead timer. This is the dead timer column. Okay. They are resetting their dead timer column. Right. But R5 is unable to do so because the interface is dead. That interface is down, and hence you can see R5 goes down, and clearly you can see here that R4 has now become the DR. And there is the earlier with R3, the state was two-way state, but now once R4 has become the DR, R3 now becomes the BDR, and with the BDR, R1 has formed a full adjacency. Okay, full adjacency. So R3 is now the BDR, R4 is now the DR. There is no R5. When there is no R5, R4 becomes the DR, and R3 becomes the BDR. When R3 becomes the DR, R1 and R2, they need to form full adjacency with BDR as well. And that is why you see here, till the time R5 became dead, R3 with R3, it was only a two-way state. The moment R5 became completely dead, it was not reachable. R4 became the DR, and then R3 became the BDR, and with the BDR, it has formed a full adjacency. It has formed a full adjacency. Okay, this is the concept of DR and BDR. And okay, and let's see that it forms a database. We were talking about database, right? So on R5, on R1, let's check on R1, and let me bring back R5. Sorry, configuration terminal, interface fast Ethernet 0/0, no shut. Okay, let's bring back R5. So once we bring back R5, it will again form adjacency, right? And OSPF messages will flow, and neighborship will be formed. Right? So on R1, okay, on R1, let's do a show IP OSPF database. We were talking about database. We discussed the database being sane, right? We discussed why OSPF is called as a link state topology. With link state, we discussed database also, right? So let's check show IP OSPF database. So over here, you can see that forget about these things. Forget about these things as of now. Just concentrate on what is given here. What is given here? Okay, we will talk about these things in detail probably in the next class. Okay. OSPF, please remember, OSPF is an important topic for anyone, even for a person who does not know OSPF at all. These things are important to understand. Okay. And if you are completely new to OSPF, and if you understand these concepts at a very great and at a very foundation level, okay, and you can impress anyone. You can absolutely impress anyone. All right. So let's just concentrate on the data that is mentioned here. We will discuss about these data, as I said, probably in the next class. So you can see here on R1, what does the database say? It says it has the link IDs of 5 routers: R1, R2, R3, R4, R5. Okay. Advertising router 1, 2, 3, 4, 5. look at the sequence number. Consider it on the sequence number 33333. Check some numbers. This link count 2. Okay, and look at this one. It also says link ID is 10.0.0.4.4.4 over here. All right, let's go to R2. Okay, R2, show IP OSPF database. You will see here R2 also has the same database. 1, 2, 3, 4, 5. Advertising in R2 1, 2, 3, 4, 5. Okay, sequence number 33333. Checksum. Okay, for on R1, what was the checksum for link ID here? 57A3. See here, 57A3, 47A6. On R2, 57A3, 47A6. Okay, look at this one, 10.0.0.4. Okay, advertising router, these things. On R1 also, you'll find the same information. Let's check on R3. Show IP OSPF database. You'll find the same information. The only thing that is changing is the age. We'll talk about this age later. The only thing that is changing is age. The rest of the things remains the same. So as I was saying, when you have the same database across the whole broadcast network, what is the point of sharing these database again and again with every router? And that was the purpose of creating DR and BDR, and that is what we had discussed in the last class. Okay, so if you do not understand this concept, what I'm trying to tell you, pause this video, go back to the previous video and listen to what I was talking about, the concept of database, and come back here. You will understand what was the reason for creating a DR and a BDR. Okay. With that, we also discussed that the information that these routers share is only with the DR. Correct. So now, who is the DR? Let's check. Show IP OSPF neighbor. Okay. Now remember that we brought back, we did a no shut on this interface. Okay. When we do a no shut on this interface, so obviously this interface comes up. R5 is live again, right? So R5 should become the DR naturally because it will have the higher router ID. Let's check that. No, it has not become the DR. R3, yeah, okay. R3 says R5 is a DR other router. R5 is a DR other router. Okay. Naturally, what should have happened when we brought back R5? R5 should have become the DR. R4 should have become the BDR. Okay. And all the other routers should form adjacency with these two routers only. Right. Oh, but over here, you can see that R4 is a DR. And since R3 has formed full adjacency with all the other routers, naturally R3 is the BDR and R4 is the DR. So when we brought back R5, when we brought up the interface of R5, okay, R5 did not become DR. This is a very good policy of OSPF. Okay, R5 will not become a DR if it comes back up. Okay, why? Because the DR and BDR are set, the database is set. Okay, R1, R2, and all the other routers have formed adjacency with DR and the BDR, current DR and BDR. So if the old DR comes up, they are not going to change their adjacency once again. They are not going to change their database once again. No, it's not going to happen. This is the condition. So if R5 again wants to be a DR, okay, if R5 again wants to be a DR, what is supposed to happen? R4 needs to fail. When R4 will fail, when R4 fails, R3 will become the DR. And then again, there will be a BDR election. And in that case, since R5's router ID will be the highest, this guy will become the BDR. Then we need to fail R3 again. When R3 fails, R5 will automatically become the DR. So DR cannot be, if the DR goes down and it comes back up again, it cannot take its position as DR until and unless the current DR and BDR fail. All right. And that is what we see here. We can clearly see R3 says R5 is a DR other router. It is not a DR. It is not a BDR. It is a DR other router. All right. Now, as I was saying that all the information, okay, let me let's do one thing. Let's bring back R5 as the DR. Okay. So to bring back R5 as the DR, let me stop all the routers and start all the routers once again so that the OSPF will start once more among these routers and R5 will automatically become the DR. I hope you guys are clear till here, right? So OSPF is running between all these routers. We will see that R5 will become the DR. Okay. And R5 will form full adjacency with all the routers. So let's give some time for the OSPF to come up. Okay, so OSPF has come up, and if we check on R1, show IP OSPF neighbors, we will see R1 has formed two-way neighborship with R2 and R3 because they are the DR other routers, and R4 and R5 are BDR and DR respectively, and with those routers, it has formed full adjacency. All right. Now on R1, okay, on R1, let us add a link. Okay, on R1, let us add a link. And here what I'm doing is capturing, I'm capturing all the information that is flowing on this interface of R5. On this interface of R5, I'm capturing all the information that is flowing. Okay. And in our last class discussion, we said if any DR other router, if any DR other router sends an information, that information will be sent at 224.0.0.5, sorry, not 5, 0.6 multicast address, which is the DR only multicast address. So if let me add one IP address on R1, that is 1.1.1.2. Okay. What R1 will do, R1 will share this as an update at the multicast address of 224.0.0.6, which will be sent to R5. It will be sent to R3, R4, R2 as well. But all of them will reject or they will not listen to this particular multicast address or multicast information. Okay. Then what will happen? R5 will share this information. R5 will share this information with all the other routers. Okay. So let me capture one more link. That is R2. This link. So I'm capturing. So I'm capturing this link and this link. Okay. This link has a DR on it, and this link has a non-DR on it or a DR other on it. Okay. And what I will do, I will add. Okay. So you can see R5 is receiving hello messages from so many other routers. Okay. We can see from R1, R3, R4, R2, R4. It is receiving OSPF messages from all the routers at every 10 seconds of interval. It is also sending its own OSPF messages as well. Okay. See here, R5 is sending OSPF hello messages as well. All right. So it is receiving, it is sending OSPF messages to all the routers in the network. Okay, the same goes for R2's link as well. It is receiving hello messages from all the routers in the network at the multicast address of 224.0.0.5. Okay, now let me add one link on R1 configuration terminal. Okay, so let me also show you the the OSPF configuration over here. So to check the running configuration on any router, you run the command show running configuration. Okay, so it will show us the currently running configuration on the device. What is a running configuration? Whatever you have configured on the device and it is currently running on it, that is the running configuration. And you can see the OSPF command that I have given is network 0000, okay, and area 0. So in our the wildcard mask session that I was taking, I explained the concept of 0.0.0.0 and wildcard mask 0000, which means OSPF will be enabled on all the interfaces and OSPF messages will be sent out of all the interfaces. But in the running configuration, this wildcard mask is shown as 255.255.255. So do not be confused as to why this is 255. Okay, when I configured it as 0000 area 0. However, in the running configuration, this wildcard mask portion is shown as 255. Okay, but the configuration remains the same. So this means that I have configured OSPF on all the routers. So the moment I configure loopback address on R1, it will also be enabled with OSPF, and that particular link will be advertised to the hello messages to all the routers. We will see that configuration terminal. Okay, interface loopback 1 IP address 1.1.1.2.255.255.255.255. Okay, now let's go on R2's this link. You will see here okay, so you will see here R1. Okay, R1 over here is sending a multicast message at 224.0.0.6. Okay, this is a link state update. We will talk about these link state updates and link state acknowledgements probably in the next class. Okay, so do not worry about it. Okay, not next class, probably in the next coming session. Okay. So 10001, which is R1, is sending, okay, is sending the link state update. Okay, it is sending the link state update of for at the multicast address of 224.0.0.6. Okay, and this is also received by R5 as well. Okay, we will check on R5. This is on R5 that we are seeing. So you can see here, it says on from R1, it has received a link state update at the multicast address of 224.0.0.6. Right now, it is advertising this particular update. You can see it is advertising this particular update. R1 sent this to R5. Okay, R1 sent this to R5. Now R1 will be sending this, not R1, R5 will be sharing this update at the multicast address of 224.0.0.5, and hence it will be received by R4, it will be received by R3, and it will be also received by R2. Okay, so you can see here it sends R1 or not R1, R5 sends this update, link state update at the multicast address of 224.0.0.5. It sends this multicast update at the multicast address of 224.0.0.5, which is the all OSPF speaking routers. And hence this update is then received by all the DR other routers. So this is how in a broadcast network, or routers where they are connected through a fast Ethernet link, database is being exchanged. Okay, so a DR other router will share the information only with the DR at the multicast address of 224.0.0.6. Then the DR will share this information with all the other routers in the network at the multicast address of 224.0.0.5. Now you may ask, what are these information? LS update, LS acknowledgement. As I said, we will talk about this probably in the upcoming OSPF session, not today. All right. And this is the reason. So, okay. So what is happening? R1 over here said, I have a new link 1.1.1.2. You should know about it. So it sent it to R5. Now on R5's database, it will also add the link of 1.1.1.2. Okay. Now what R5 will do, R5 will share this update to R4. It will share this update to R3. It will also share this update to R2 as well. So on R4's database, it will also have 1.1.2, 1.1.1.2, and 1.1.1.2 on all the other routers as well. Let's check that. Okay. So on R1 database, show IP OSPF database. Okay. You can see give me a minute. All right, my bad. What happened is I typed a wrong command when configuring IP address over here. So if you see here, 1.1.1.1 was already loopback 1, right? It was already loopback 1. But the moment I typed loopback 1 as 1.1.1.2, the IP address of 1.1.1.1 got overwritten by 1.1.1.2. Okay, so let me add a new interface loopback to, okay, IP address 1.1.1.1 255.255.255.255. Okay. Now on R1's interface, show IP OSPF database. Okay, and show IP OSPF database router. Okay, so over here you can see that R1 says it is connected to two links. Okay, it is connected to three links. One is the loopback 1, the other is the loopback 2. Okay, and then it is connected to a broadcast network. That broadcast network is called as a transit network. That broadcast network is called as a transit network. Okay, and in that broadcast or a transit network, the router with the IP address of 10.0.0.5 is the designated router. Okay, so do not worry. My intention to show you here was on R1's database, it now has two loopback addresses, 1.1.1.1 and 1.1.1.2. Obviously, what R1 is going to do, R1 will share this information with R5. R5's, let's check on R5. Does R5 also has this information? Okay, show IP OSPF database router 1.1.1.1. Do not worry about these commands. Okay. Here also you can see R5 now also knows about 1.1.1.2 and 1.1.1.2. Now what R5 is going to do? R5 is going to share this information with R4, R3, and R2. Okay, let's check on R2. So R2 now also knows about 1.1.1.1 and 1.1.1.2. So this clearly proves that though R1 did not had full adjacency with R3, R4, R2 and R3, still R2 was able to get the information of 1.1.1.2 and R3 was also able to get the information of 1.1.1.2 in their database. Okay. So the commands that I told you, do not worry about those commands. We'll talk about those commands in detail when we will be discussing, as I said, the link state update, link state acknowledgement that we saw in the Wireshark capture. Okay, I know OSPF is a long topic and it is being dragging since long, but this drag is absolutely necessary for you guys to understand the concept of OSPF and to have a great base and foundation about OSPF, so that when advanced concepts are taught to you, you are able to understand it clearly. And this is absolutely necessary even for you guys to clear the interviews as well. All right. So this is what happens in the broadcast network. All right. So with this, we are done with the OSPF on Ethernet links. Okay. So let me go back. Right. Now, tomorrow we will discuss about areas. Okay. Tomorrow we will discuss about areas. Why OSPF uses areas and why is it necessary for OSPF to work with areas and how areas basically help OSPF to scale in a larger network environment. All right. So with this, I will stop the recording and have a great day and have a great night. Bye bye. Thank you. See you tomorrow.